Quantum gravity is one of the most exciting and mysterious areas of modern physics. It attempts to combine the two pillars of science, quantum mechanics and the general theory of relativity, into a single theory that will explain how gravity works on the smallest scales. To date, this task remains unsolved, but scientists have made significant steps toward understanding it. Let's look at what quantum gravity is, why its study is so important, and what hypotheses and theories it includes. What is quantum gravity? Gravity is the force that is responsible for the attraction between objects. On large scales, such as planets, stars, and galaxies, gravity is perfectly described by the general theory of relativity developed by Albert Einstein. This theory explains gravity as a curvature of spacetime caused by mass. However, at subatomic scales, where the laws of quantum mechanics apply, the general theory of relativity no longer works. Quantum mechanics describes the interaction of particles at the level of atoms and below, but it does not take gravity into account in any way. Combining these two theories into a unified system is the main goal of quantum gravity. Why is quantum gravity so important? Black holes. Quantum gravity is essential to understanding the nature of black holes. At the center of a black hole, at a point called a singularity, the density becomes infinite and the laws of the general theory of relativity no longer apply. We need a new theory to describe what happens under these extreme conditions. The origin of the universe. Quantum gravity can help answer questions about the beginning of the universe. The Big Bang theory suggests that at the moment the universe was born, all matter was concentrated in an infinitesimal point. Understanding these first moments requires a theory that combines quantum mechanics and gravity. A theory of everything. Quantum gravity is an important part of attempts to create a theory of everything, a unified theory that explains all the fundamental forces of nature: gravity, electromagnetism, strong and weak interactions. Main approaches to quantum gravity. To date, there are several theories and hypotheses attempting to describe quantum gravity. Each of them offers a unique perspective on the problem. String theory. String theory proposes that all the particles we see are actually made up of tiny vibrating strings. These strings can vibrate in different ways, creating different kinds of particles. String theory combines all the forces of nature, including gravity, into one mathematical approach. In string theory, gravity arises from a particle called a graviton. This hypothetical particle carries gravitational interaction, similar to the way a photon carries light. Loop quantum gravity. Loop quantum gravity offers a different approach. It views spacetime as consisting of discrete quanta. Think of spacetime as a grid or fabric made up of tiny cells. This theory states that spacetime is not smooth, as in the general theory of relativity, but has a granular structure. One implication of this theory is that there is a minimum length below which it is impossible to look. This idea is related to the concept of the Planck length, which is approx. 1.6 times 1035. Holographic principle. The holographic principle is a concept that suggests that information about a three-dimensional space can be encoded on its two-dimensional surface. This idea originated from the study of black holes and proposed that all information trapped in a black hole is stored on its event horizon. The holographic principle can help explain how quantum mechanics and gravity interact with each other. Quantum theory of gravity based on asymptotic safety. This approach assumes that gravity can be described quantum mechanically at certain high energies. The theory claims that gravity remains safe in the sense of mathematical consistency even on small scales. Experiments and observations. For now, quantum gravity remains a largely theoretical field, but scientists are looking for experimental ways to test it. Gravitational waves. Observations of gravitational waves from observatories such as LIGO and Virgo may give us clues to understanding the quantum effects of gravity. Cosmic microwave background. Studying relic radiation left over from the Big Bang may provide clues about quantum processes that occurred in the early universe. Quantum experiments. Modern experiments with particle entanglement and superconducting quantum circuits can provide clues about the nature of gravity at the quantum level. Challenges of quantum gravity. Despite significant progress, scientists face serious obstacles. Lack of experimental data. Gravity is so weak compared to other forces that its quantum effects are extremely difficult to measure. Mathematical complexity. Theories such as string theory and loop quantum gravity are incredibly difficult to analyze mathematically. Competing theories. There is no single approach that completely meets all requirements. Each theory has its own strengths and weaknesses. Quantum gravity is the key to understanding the most fundamental questions about the universe. It lies at the intersection of quantum mechanics and the general theory of relativity, two of the greatest achievements of science. Despite the challenge, scientists continue to explore this field, and each step brings us closer to answering questions about the nature of time, space, and gravity. If you're interested in learning more about such fascinating topics, subscribe to the channel, give us a like, and share your thoughts in the comments.